Okay, all right. Good afternoon, everyone. Hopefully, all of you are doing well today. It's a great pleasure for me to welcome all of you. Thank you for making the time to watch our webinar today. First of all, on behalf of our Barampur Girls College, I'd like to welcome all of you to this prestigious webinar about fluorescence spectroscopy, its application in chemistry and bioscience. Recently, coronavirus pandemic has come back again and imposed restrictions on many of our offline academic activities. At least today we are today is going to be a great day for all of us because we are impatiently waiting for this meeting to enrich our insight and knowledge regarding this topic. It's especially a great moment for us to have Professor Pradeep Singh, today's keynote speaker, today's resource person, Dr. Nimai Misro, Dr. Pavel Banerjee. On behalf of Department of Chemistry, I like to welcome all of you. Another resource person, Dr. Ranjan Chakraborty, won't be able to deliver today's presentation. Unfortunately, he has been infected by coronavirus, so one person will not be able to speak today. Also, Honorable, I like to welcome Honorable President of Government Body, Barampur Girls College, Professor Minal Kanti Chakraborty. Honorable Principal of our college, Dr. Hena Sinha, all the participants, colleagues, faculties, and students. I like to thank you, all of you, for making a time and participate on this event. I want to thank all the organizing committee member, Dr. Khaibar Ali Mia, Associate Professor in Political Science Department, Professor Subhasri Chakraborty, IQACU Coordinator, Dr. Siddhiratan Tripathi, Associate Professor in Physiology, Dr. Shomik Mondal, Dr. Gopam Barman, Dr. Nimai Saha, Assistant Professor in our department, Dr. Paramita Mondal, Associate Teacher in our department, Chandana Mukhopadhyay. I would like to thank Dr. Mohammad Iqbal, Assistant Professor in Department of Chemistry. He also joint coordinator who has been put together most of the work for today's webinar. I am sure most of you know the organized committee member. Alas, let me introduce myself also. Maybe most of the people don't know me. My name is Rajiv Pramanik. I am the Assistant Professor in Department of Chemistry. I am the coordinator of the today's program also. For your information, we are live broadcasting this program through online YouTube channel. So if anyone missed out the program for any technical or other reason, they can always watch it later. You can find the recorded version by searching the title in YouTube. The main goal of today's webinar conducted by Chemistry Department is to inspire students to engage in this relevant and informative research learning process to better understand the role of scientific research in the modern world, take home some scientific message, learn some scientific language, generate curiosity about science, so that they can motivate further science and technology and choose research as a career. In this way, they can contribute in science and nation building, which our country desperately needed. The title of today's webinar is Fluorescence Spectroscopy, its application in chemistry and bioscience. In order to cover this broad topic, we are fortunate to have two experts in respective research field. Joint coordinator Dr. Mohammad Iqbal will chair the scientific session. We will introduce each speaker one at a time before their presentation. Our first speaker, Dr. Nimai Misra, will talk about the prescribed nanoparticle synthesis, stability, and application in light emitting diode. And another speaker, Dr. Pavel Banerjee, will talk about the topic change in lipid bilayer properties, a mysterious avenue towards origin of life. This is about the scientific session. You will get the more details from Dr. Mohammad Iqbal at the beginning of this session. Also, I note that we have provided the um, event feedback Google link. So please go through the link and gives your valuable feedback. We'll really appreciate that, as it will assist us better organize the future event. Okay, so let's get started. So, Professor Minal Kanti Chakravarti will inaugurate the event. So I'd like to invite Professor Minal Kanti Chakravarti to give the inauguration talk. So virtual machine is over to you, Dr. Minal Kumar Chakravarti sir. স্যার আছেন? হ্যালো,
দেবজ্যোতি নামে কোনো আছে? দেবজ্যোতি তো ওখানে সাপোর্ট দেওয়ার কথা।
না উনি দেখতে পাচ্ছি না তো। না ম্যাডাম ওনাকে তো দেখতে পাচ্ছে না।
আসছে লিংকটা বিভ্রান্তি ঘটেছিল, লিংকটা আমিও বিভ্রান্ত হয়েছি। আমরা অন্যটাতে ক্লিক করে পাই চট করে, এটা হচ্ছে না, জয়েন করছে, এক্ষুনি ঢুকবেন।
আচ্ছা ঠিক আছে। হ্যাঁ স্যার বলুন, স্টার্ট করুন। স্যার আপনি স্টার্ট করতে পারেন।
স্যার আপনি ইনঅগ্রাল স্পিচ দিয়ে দিন, ওরা আগে বলে দিয়েছেন, আপনার জন্যই অপেক্ষা করছিলাম। স্যার
আমাকে বলছো?
হ্যাঁ স্যার।
নাকি আমাকে বলছো?
হ্যাঁ স্যার, স্যার আপনি ইনঅগ্রাল স্পিচ শুরু করুন, ওরা বলে দিয়েছেন অ্যাঙ্কার, আপনার ঢুকতে একটু দেরি হলো তো। স্যার শুরু করুন। হ্যাঁ হ্যাঁ স্যার।
আমি কি শুরু করবো না?
হ্যাঁ আপনি শুরু করুন স্যার, শুরু করুন।
আচ্ছা। Respected distinguished guest speakers coming from different university of Avanti and outside. Respected professors and officer of this college, respected Principal Dr. Hena Shena, who heads and leads her best to organize such prestigious national level seminar, and our favorite students, especially of the Department of Chemistry. I beg to be excused to our guest speakers, as I am in some sense technically inconvenient position to mention their individual names, which is definitely a fault with me. So once again, I beg to be excused. Our speakers of this seminar are scholars of high repute. They are distinguished scientists in their respective fields. And Bahrampur Girls College is proud to have such speakers, and their speeches and results of researchers and so on. We all know that the world is passing through a great very deadly danger we are facing now. But Bahrampur Girls College, in conformity with a long tradition, doesn't know to stop. Surpassing all barriers and obstacles, this college is always on the line of progress. Maybe retarded for some time, but it is highly compensated by the acceleration later on in this process of progress. Today's organized seminar undoubtedly will add a new jewel to the crown of this college. Respected audience of this seminar should know that Girls College Bahrampur is a name in the history of higher education in our state. It enjoys a special map, a special point, special spot on the map of this country. And I am privileged to have this opportunity to inaugurate this memorable August seminar, from we shall learn many things about science and its special branch chemistry, which owes a long history in the search of civilization and knowledge. It is a core subject, and it dates back to even before Christ in the West. and some 1,000 years before in our country, India. This seminar on the subject printed on our invitation card and addressed by our scholarly speakers will enrich the minds of our students, teachers, and all the attendants. I wish it success. Once again, I say I am proud of inaugurating this seminar. I announce the inauguration of this seminar. Thank you all.
Thank you, Professor Minal Kanti Chakraborty, for your wonderful innovation talk. Now, I'd like to invite Dr. Hena Sina, Principal of Barampur Girls College, to give the welcome address. So, the virtual machine is over to you, ma'am.
Namaskar. Good afternoon to all of you. I, as patron of the webinar and principal of Barampur Girls College, welcome you all to the one-day national webinar on fluorescence spectroscopy, its applications in chemistry and bioscience. Organized by the Department of Chemistry under the guidance of Internal Quality Assurance Cell of Barampur Girls College. Present amongst us is the chief patron of the program, Professor Mrinal Kanti Chakraborty, Honorable President of the governing body. As chief guest, we have Professor N.D. Pradeep Singh, Department of Chemistry, IIT Kharagpur. As research persons, we have Dr. Anjan Chakraborty, Associate Professor, IIT Indore. Dr. Nimai Mishra, Assistant Professor, SRM University, Andhra Pradesh. Dr. Pavel Banerjee, Professional Research Scholar, University of Copenhagen, Denmark. I congratulate the initiative of the Department of Chemistry to sustain the teaching learning scenario in the time of pandemic. I also congratulate the initiative of the coordinator, Dr. Rajiv Pramanik, and the joint coordinator, Dr. Iqbal Ahmed. I welcome the teachers, non-teaching staffs, and students of the college to today's national webinar. Thank you. Namaskar.
Thank you, madam, for your excellent welcome address. Now, I'd like to invite Professor Sushi Chakraborty.
Research persons, we have Dr. Anjan Chakraborty,
Associate Professor, IIT Indore.
হ্যাঁ,
Actually একটু প্রবলেম হচ্ছে ম্যাডাম এখানটায়।
ইউটিউব চ্যানেলটা কি খোলা আছে পাশে? ওই জন্য সাউন্ডটা আসছে, বন্ধ করে রাখো।
একটা প্রবলেম হচ্ছে। So I would like to invite Professor Subhasit Chakraborty, IQAC coordinator of Bahrampur Girls College, to give the address. So Dr. Professor Subhasit Chakraborty, the microphone is over to you.
Am I audible?
হ্যাঁ ম্যাডাম শুনতে পাচ্ছি।
আচ্ছা, ঠিক আছে। A very good afternoon to all of you. Honorable President of the governing body of our college, Professor Mrinal Kanti Chakraborty, respected Principal Madam Dr. Hena Sinha, Honorable Chief Guest of today's program, Professor N.D. Pradeep Singh, Professor, Department of Chemistry, IIT Kharagpur, distinguished resource persons, Dr. Anjan Chakraborty, Associate Professor, IIT Indore, Madhya Pradesh, Dr. Nimai Mishra, Assistant Professor, SRM University, Andhra Pradesh, and Dr. Pavel Banerjee, Postdoctoral Researcher, University of Copenhagen, Denmark, my esteemed colleagues, students, and other research fellow, and all the participants who have joined through the virtual mode. I, as a coordinator of IQAC of Bahrampur Girls College, take this opportunity to welcome you all in the one-day national webinar on fluorescence spectroscopy, its application in chemistry and bioscience, organized by the Department of Chemistry of our college. On this occasion, it is my privilege to say something about our college and the role played by the IQAC of our college towards achieving the goals of higher education. Bahrampur Girls College, founded in 1946 and located in the heart of the district town, has emerged as one of the premier institutions of West Bengal, with an aim to disseminate the message of higher education in the region of underprivileged people. At present, the college is celebrating its Platinum Jubilee year. Our college, with its disciplined environment and robust academic tradition and cultural values, has been serving the need of the society by inculcating the motto of this institute, Sha Vidya Ya Vimuktaye, which means that it is education which helps to attain salvation. With changing situation, the institution has assimilated the modern value of education and made a bridge between the past and the present so that the learners may grapple with the challenge of the rapidly changing society. The IQAC of the college enacts a leadership role by assuring the progression of academic culture in the institute. It deserves mention that a large number of students come from the rural areas of the district of Murshidabad and some other neighboring districts with the ambitious hope of progression in education. Moreover, in the last few years, a large number of first-generation learners are coming to our institution. Thus, our focus is on promoting a positive academic environment that emphasizes critical thinking, encourages creativity, and develops a sense of social responsibility among the students coming from rural background. At the same time, we also keep in mind the employability factor of the girl students. Thus, efforts are made to impart ethical and value-based traditional knowledge as well as transferable skill so that after graduating from this college, the students will be able to grab the opportunities available to them. Students are often encouraged to take part in co-curricular and extracurricular activities beyond the campus, which gives them a good exposure and builds self-confidence. The IQAC of the college aims to create a fertile ground for research orientation among the teachers and advanced learners. We are also planning to increase interdisciplinary research activities. On the basis of the recommendations made by the IQAC, the governing body has approved the provisions for institutional research grant, seminar attendance grants, etc. I hope that this kind of financial assistance will encourage and motivate the young faculty members as well as the interested students towards research work. Accordingly, students are encouraged to take dissertation paper in the final semester. The IQAC also facilitates and encourages different departments to organize workshops, seminars, webinars, and etc. In this prospect, I am very happy that the young faculty members of the chemistry department have organized this webinar. I extend my best wishes to Dr. Rajiv Pramanik, coordinator of this program, who have recently joined our college, and Dr. Mohammad Iqbal, joint coordinator, for organizing this webinar, and the entire team of the chemistry department for their constant support for making this webinar successful. I sincerely hope that the valuable deliberations made by the distinguished professors and speakers will enhance the knowledge base of all the stakeholders. I wish every success of today's seminar. Once again, I thank the organizers for giving me this opportunity to share my views with all of you, and thank you all. I hope everybody will be eligible to get valuable information from this seminar. Thank you once again. Thank you all. Rajiv, please continue. I think some technical glitches are going on. That's why they are not able to manage the things in right way. Rajiv, Iqbal, are you here? Just a second. Let me call them.
Yes, Didi, I'm here.
Please continue.
Yes, yes.
Thank you, madam. Any problem in internet? I'm sorry about that. Thank you, Dr. Subhasri, Professor Subhasri Chakraborty, for your excellent introductory talk. Now, the Department of Chemistry, head of the Department of Chemistry, Dr. Gopal Varman, won't be able to speak today because he's not feeling well today. So we'll move to the next keynote speaker. It's my great pleasure to introduce Dr. Uh, Pradeep Singh, our today's webinar keynote speaker. We are honored by this afternoon by presence of Honorable Dr. N.D. Pradeep Singh, Professor of Chemistry Department, Indian Institute of Technology. Professor Singh has completed PhD from University of Madras in year 2001. After completion of his PhD, Professor Singh has pursued his first postdoctoral research from 2002 to 2005 at the University of Cincinnati, Ohio, United States, followed by his second postdoctoral research from 2005 to 2007 at the University of Leeds in United Kingdom. 2007, Professor Singh has joined Department of Chemistry, IIT Kharagpur as an assistant professor. Since then, he has been actively involved various research activity, mainly synthesizing and designing organic nanoparticle to develop nanocarrier for drug delivery. He has published many papers in reputed international journals. Dr. Pradeep Singh is not only as an excellent scientist, but he also is a wonderful teacher. Many of his students has already established in many uh, uh, universities all over the India. We are fortunate that one of his students has joined in our department as assistant professor. Now I request Dr. Pradeep Singh to address the keynote speech. So the virtual microphone is over to you, sir.
Thank you, Rajib, for your small and nice introductory remark about me. So I'm audible, right?
Yes.
Yes. Okay. So it looks like it's sort of homecoming because I have two students whom I know earlier, like Rajib Pramanik and Mohammad Iqbal. Both I know them personally, so it's good to get back to this college. Yeah. So at first, I like to thank the coordinator, Dr. Rajib Pramanik, and the joint coordinator, Mohammad Iqbal, for calling me and giving me an opportunity to be a part of this wonderful national seminar entitled as Fluorescence Spectroscopy and its application in chemistry and biology. I also sincerely like to express my thanks to Professor M.K. Chakravarti, the Honorable President of the Bragampur Girls College, and the Principal, Dr. Enna Sinha, for asking me to give a keynote address on this seminar. And finally, more important, I want to convey my best wishes to this energetic, stimulating undergraduate student of this Bragampur Girls College. Being a keynote address speaker, it becomes my duty and responsibility to convey my thanks for all the technical speakers, including Dr. Anjan Chakravarti from IIT Indore, Dr. Nirmay Mishra from SRM University, Andhra Pradesh, Dr. Pavel Banerjee, who is currently doing a postdoctoral research in Denmark. So thanks all of you for accepting this invitation, and you're kind enough to give a talk here. I'm really confident that your talk will be stimulating and your talk will pave a road map for these undergraduate students to get into research. So that's my first part. This is always people talk when you are a keynote address. You want to thank all of them who are involved in this. If I miss anyone, my sincere apologies. And I thank everyone all the team members for initiating this national seminar. Once I look into this national seminar program, I want to really appreciate from my heart both the coordinator Rajiv Pramanik and Muhammad Iqbal, along with the principal, to start this initiation in a college. I know for sure that this national seminar will have two big outcomes. The one outcome I personally feel is that this national seminar will give a big roadmap for these undergraduate students to know what are the research activities which are currently going. So this will put them towards research. That's a first outcome I think this national seminar will be doing on. As a personal note, since it is a girls' college, I want to say that after 2007, when I joined Department of Chemistry, IIT Kharagpur, and now it is 2022. So I personally feel that the number of students, girl students in particular, are increasing year by year. So, and that also, if you look into the organic synthesis part, I can see that the number of girl students are day by day increasing, which is really a good thing. Not to take any other example, taking an example from my research group itself, if you look like more than 20 PhD students would have graduated from my research group so far. And half of them are girl students. And they are now very successful. Most of them are doing their postdoctoral in abroad, in US, Germany, Japan, and some of them have already become as a faculties in some reputed institutes. So I think that there's a huge scope for these girl students to get into research. So I personally feel that this national seminar will help this young, brilliant mind to get into research activities. Because at the end of the day, you are the pillar for our research. Whatever we think, if our research scholars have to actually demonstrate in the lab. So you are the pillar of the research. So we want you guys to get into the research. Okay, so I profoundly feel that this seminar will have a great impact on you guys to get into research. The second outcome of this national seminar, what I think is that, which has been initiated by these two coordinators, what I personally feel, it will sort of cultivate, or it might initiate the research environment in the college. I know that doing a research in a college is not that easy because you don't have the infrastructures. Since we are gifted, we have infrastructure, we do research. But it's very hard to do research in local college, which I really know that. So I think this type of seminars will help to get along, to have a nice international collaborations or collaborations between the reputed institutes and the colleges, so that the faculties who are newly joined in this college can write a collaborative project, submit in funding agency, get money, and start their research. So I think this will be a very important thing, because this type of initiatives is really needed if you want to initiate a research in local college. So I personally feel these two things will be a right outcome of this national seminar. One, as I said, it will make this young minds to get into research. And the second thing, it will initiate a research, or it will cultivate a research environment in the Bragampur College. So for that, I also say that all these students should be grateful and should be thankful to your coordinator and to your principal for such a nice initiation. Fine. This is all about what this national seminar is going to do for you. Now, getting back to the science. Once I looked into this technical session, or I looked into the title of this whole theme and everything. And if you see, this is more about the fluorescence spectroscopy and exploring its application in chemistry, biology. I don't know why they missed materials, but anyhow, that's good that chemistry and biology you have interlinked. So that's a very nice theme to be selected. And if you look, and this is the right and exact timing of this specific theme of this national seminar. Why I said is that if you look into the late great scientist N.J. Turo, he said that the next 50 years is going to belong to photophysics and photochemistry. So I feel personally that this is the exact and apt theme to be discussed. So I really appreciate the coordinators for selecting this wonderful title to be discussed. So getting seriously about fluorescence spectroscopy, a little bit more technical. Since I am keynote address, I want to get into a little bit technical about this fluorescence spectroscopy. See, if you look into different spectroscopic techniques like UV absorption, which you have known, colorimetric, as well as fluorescence spectroscopy, you can see this, the application of this fluorescence spectroscopy. It was like in 1960s, 70s, people used fluorescence spectroscopy mainly for understanding the excited state nature of the chemistry. But in last 2 decades, the application of fluorescence spectroscopy has went into different dimension. People have used this fluorescence spectroscopy for diagnosis diseases, which is very interesting. They are used to real-time monitor the drug release inside the system. That's another important application of this fluorescence spectroscopy. And then people have used this for material applications. People use this fluorescence sensing for environmental, mainly for sensing heavy metal ions, sensing some aromatic pollutants. And this has become very interesting. And if you look as a student, you should ask yourself why this fluorescence spectroscopy has become so much importance compared to this UV absorption spectroscopy or other things. So any student who know what is the reason why this fluorescence spectroscopy is taking a different dimension and going to the next level? Might be you have not studied fluorescence spectroscopy. Any students? Nothing wrong. I want a wrong answer. Okay, fine. That's okay. The main reason, if you look into this, the 2 main reasons I talk about fluorescence spectroscopy. One is that its sensitivity. It has a very high sensitivity. And the second is its high selectivity. So having a spectroscopy which has 2 hand-on-hand, sensitivity and selectivity, makes it very interesting. And second, anyhow, fluorescence spectroscopy is you cannot say cost effective, but it's still compared to others is cost effective instrument, and it is easily operatable. So the main high sensitivity and selectivity makes this fluorescence spectroscopy very demanding. Okay. So anyhow, all these things your technical speakers are going to tell you in detail. So we will get. So recently I was looking into a review article. Non-destructive as well. Yeah, UV spectroscopy is also non-destructive. But anyhow, I will get that point. It's a nice point. Suparna, nice. The another, the fluorescence spectroscopy is good, that it's a non-destructive technique, but UV, this also is a non-destructive technique. I think high sensitivity and selectivity takes the major importance of this instrument. Okay, fine. Recently, I looked into a review article. I was studying about fluorescence spectroscopy, and I found one nice thing. They have now, it's a Japanese, both Japanese and as well as Chinese group. They have made a smartphone inbuilt fluorescence spectrophotometer, which is a portable using this AIE and deep machine learning. They have made this nice smartphone portable fluorescence spectroscopy. And using this smartphone fluorescence spectroscopy, they were able to sort of image virus, bacteria, and as well as they were able to even see this RNA slicing and sequencing, which are very interesting to look into it. So it has really grown up and went to the next stage. So so it was really a good topic to be taken as a theme and needs to be discussed. Okay. So if you don't mind, because whatever I said, yeah, it will be people can comprehend from the higher level, but for undergraduate students, I don't know whether it is easy for you to comprehend what I said. I can show some images if you want to know. Iqbal, can I show some slides if I have time? Rajiv?
Yeah, yes, sir. Sure. Yes, sir. It will be really great for us.
Okay. So I will show you some work which have been done from our lab so that you can really enjoy what I am talking about. Okay. So your entire screen. I don't know. Can you see this, Iqbal?
Yes, sir. Very much.
Yeah. Okay. Thank you. So this is mainly for this undergraduate students.
Sir, can you please make it a slideshow, please?
Yeah. Sure. I can just a minute, Iqbal. Yeah. Now it's okay.
Yes.
Yeah. So we call this as a perlin molecule. This is mainly for undergraduate students. So we took a perlin molecule. This is a nice red fluorescence. Okay. And this is an anti-cancer drug, chlorambucil. Okay. So nothing we did. We attached this to it's a simple esterification reaction, which you have studied in your undergraduate. It's an esterification reaction. Now this we call as a drug delivery system. You call them as a prodrug, whatever you want. So before getting into it, what we did is that we made them as a nanoparticle. Don't get into more technical. We just made them as a nanoparticle. And if you see the size of these nanoparticles, this is organic nanoparticle. It's not inorganic. It's an organic nanoparticle. And if you look into the size of these nanoparticles, they are around like 10 to 20 nanometers. Now, once we made this system, this drug delivery system as nanoparticle, what we did is that we took this and we incubated. That means without non-technically, we put them together in the cancer cells. Okay. And then after 3 hours, we took the image. You can see that this is the cancer cell. And as I said that the fluorophore which we use, that perlin, is a red color. And you can see here, but this is a complete confocal fluorescent imaging. Okay. And you can see now how these nanoparticles are getting inside the cancerous cell. So this is a contrast image. You can overlay and see out where these nanoparticles are exactly went. So that's how you can do the imaging. You can find out how your drug delivery system, how the drug is getting inside the cancerous cell. And this type of thing you can get only from fluorescence spectroscopy. Okay, this is one example. I will show another example. So what we did is that most of these nanoparticles, if you look in these images, they are all like completely scattered over the cell. We thought, why cannot we make a drug delivery system which can go exactly to the nucleus of the cancerous cell? So for that purpose, we took this acridine, okay, which is again a fluorophore, and then we attached the anti-cancer drug chlorambucil, and finally we made them as nanoparticles. These are all shape of 20 to 30 nanometer. And then we took an image. And you can see from the image, okay, this is the cellular image. And you can see from this images very nicely. You see this is a complete cell. And you can see the nanoparticles are completely localized on the nucleus of the cancerous cell. So now you can selectively target the organelle of the cancerous cells. I'm showing an example where you can target the nucleus. Even you can target the mitochondria, you can target lysosomes. We have targeted like that specifically the organelle of cancerous cell. But whether you targeted or not, how to know? This is a simple fluorescent experiment you do and you learn about techniques. That's why I said this fluorescent gives you so much importance. And these are all basically a 2-photon confocal microscopy. That's why your depth penetration will be much more easier. And you can say that, sir, it's only cancerous cell. No, we have also made nanoparticle DDS, which can be also used for imaging bacteria and viruses. So this is a sort of Pseudomonas aeruginosus bacteria, and you can see that each bacteria, you can see the nanoparticles are nicely getting into the bacterial cells. Another application I can show that we also made nanoparticles which are used for agrochemicals. People were asking us, sir, all the time you are doing this cells, bacteria, cancerous cell, why cannot you do application differently? So we have used a nano formulation for agriculture, and you can see that using these nanoparticles, we are able to image the xylem and the phloem of the plant cell. So you can even image the plant cell and see how this pesticides or the plant growth hormones are getting inside the plant cell. So that's why I'm saying this technique is wonderful technique. Okay, you can see that how this pesticides are killing the xylem and phloem part of your plant cell. So like that, we can do okay. So that's how there are many applications, and I hope that your next 3 speakers will talk all about these things in detail. But as a keynote, I want to just mention certain things, how this confocal microscope can be really useful in different applications, starting from biology to environment. And we also work on this. And using this confocal microscope, we also see how the drug is delivered inside the cancerous cells in real time. Okay. So with this, I like to conclude my keynote address. So I want to wish that this seminar or this national seminar should be very successful. And I wish both the coordinators in future also to come up with this type of national seminar, so that it will be helpful both from the student point of view and from the faculty point of view. So very thankful for giving me this opportunity, and thanks a lot.
Thank you, Professor Pradeep Singh, for your insightful talk about the fluorescence spectroscopy. We are really fortunate to have you. It will definitely encourage us to do more science on spectroscopy and organic chemistry. Also, I'm sure after hearing your talk, many of our students will gravitate towards science. So thank you, Dr. Pradeep Singh, once again. Now, we'll move to our next program. So we'll move to the scientific session now, talk session. And Dr. Mohammad Iqbal will anchor this session. So I'll ask to Dr. Iqbal to take over this session. Mohammad Iqbal, you can continue now.
Thank you very much, Dr. Pramanik, for nicely chairing the session. A very good afternoon to all of you. Myself, Dr. Mohammad Iqbal, Assistant Professor, Department of Chemistry, also joint coordinator of this webinar. It's my pleasure, it's my honor to be part of this program. On behalf of Chemistry Department and Brahmanpur Girls College, I welcome once again all of you in this virtual platform. In the today's technical session, we have 3 speakers, but unfortunately, our first speaker, Dr. Anjan Chakraborty, cannot present his talk because he got affected by COVID-19. We pray for his speedy recovery. So we have little change in our time schedule. So I will request our next speaker to come forward and to present. So our first speaker will be Dr. Nimai Mishra, Assistant Professor, SRM University, Andhra Pradesh. Dr. Mishra has completed his BSc degree in chemistry from University of Bardwan in 2005. Then he did his master's from Indian Institute of Technology, Madras, India in 2008. After completion of master degree, he went to Singapore to get his PhD degree, and from National University of Singapore, he obtained his PhD degree in 2013. After PhD, he did his first postdoc from Los Alamos National Laboratory, USA, from 2013 to 2016. After that, he did his second postdoc from Italian Institute of Technology, Genova, Italy. There he stayed from 2016 to 2017. Dr. Mishra has published his research work in many reputed international journals with very high impact factor. The research interest of Dr. Mishra in the field of perovskite, nanocrystal, quantum dot synthesis, stability, and their application in LED. With this short introduction, now I am requesting Dr. Mishra to start today's presentation. Dr. Mishra, please, the virtual mic is up to you now. Sir, we are not audible.
I'm muted. Okay. Yeah. Thank you, Dr. Iqbal, for your kind introductions. So I'm okay now, Dr. Iqbal? It's clearly audible?
Yes, very much.
Let me share my PPT. Now, thing is, I can't. Can you guide me once? Because we have been using Zoom and we're not much using this one. I can see the share option and then.
Yes, there is a arrow sign, so you can click there.
Yeah, can you
now?
Yeah. Can you see now?
It's coming. Yeah, it's visible now. Yes.
Okay. Yeah, you can see my screen, correct? My slides.
Yes.
Yeah. Okay. Thank you so much. So let me see. I think as Dr. Rajiv Pramanik told me, I should speak for around around 20 minutes, correct? And then followed by some question and answer. Okay, first of all, thank you so much to the organizer and to the principal of Baharampur Girls College, all the faculty members there, and keynote speaker, Professor Singh from IIT Kharagpur. It's very pleasure to be with you, sir, here. And also like to thank both the organizer, Dr. Iqbal and Dr. Rajiv Pramanik. I particularly like to thank to Rajiv Pramanik. Rajiv and myself are we are very good friend. We spent lots of good memories in Los Alamos lab. We spent 3 years together, so we had lots of good memories. So when Rajiv was thinking about this seminar, he called me because my work also in Western mostly I use fluorescence spectroscopy. And so I thought, I'll be delighted to give a talk where Rajita is working. Hopefully we can go to physically, but in current situation is prevailing, we're not able to do so. So anyway, thanks to Rajita, thanks to Dr. Iqbal and Department of Chemistry, other colleagues for organizing this wonderful seminar. And that could be useful for undergraduate students. I believe mostly the undergraduate students are there. As Professor Singh has rightly mentioned, that it will promote the research environment atmosphere in the college, though it is having lots of difficulties, chronic underfunding, and there is not much instrument facility. Not much means not at all. Maybe instrument facilities there, but through this kind of program, we can get to know each other. And today's world is very much collaborative in nature, so we can able to do some they can do some work together. So as you know that in the foreign universities like US and the Western worlds, and also have seen in Singapore, the undergraduate research program is very strong. The undergraduate colleges, they have very good research program. Slowly the things are coming up. I think in our curriculum, the new education policy also says that our undergraduate program should have a research component, and it might be having a 4 years program very soon. So this is one of the positive direction. I think we are a degree college. We are been underprivileged in a sense that BTech program is 4 years when students can directly go to PhD program. Wherever we are barred to do a master's in between. But ISAR has made those changes. They have this 4 years and 5 years BSMS program. So slowly we are moving that strong undergraduate research curriculum. And again, going to today's discussions, first of all, নতুন বছরের সবাইকে অনেক শুভেচ্ছা, সবাই ভালো থাকুন. I wish all of you very happy new year, and also wish currently we are undergoing the third wave, and that is unfortunately drastically it is happening in West Bengal along with Mumbai and Delhi right now. It is going to happen all over India. Unfortunately, things are again going beyond control. Kindly, my request to all the students, you try to become, watch out for your family, neighbors. So you guys are the pillars. You guys see that people wearing masks properly, sanitize properly. That's the only way we can save. We had very bad memories in the second wave in the April, May in the 2021. We thought 2022 will bring new happiness, new prosperity, but unfortunately again our country and as all over the world, we are under this threat. As you can see, one of our speaker, Anjanda, is also got infected. Hopefully we can come over from these things. That's the hope. Without hope nothing can be done, and things will be normal very soon. Let's that's the hope. So now let us discuss, as the overall the topic is fluorescence spectroscopy and its applications. I am going to show you some of the interesting results and interesting research that we are pursuing here. As Dr. Iqbal has said, that I'm currently working in a SRM University AP. You can see in this image, this is our newly constructed campus. Our university has started in 2000. Let me sharing the pointer. Yeah, in 2017. You might heard of SRM Chennai, which is one of the biggest SRM university, one of the biggest university in terms of private university in terms of engineering educations. But this is completely a new university located at Vijayawada at Andhra Pradesh with aiming engineering, sciences, laws, medical law and medical school, pharmaceuticals all together. This is one of our main academic building. Besides few more research blocks, it has come up. There are hostels. We had made incredible good infrastructure in last 4 years. Our first batch is just now out, and we have guiding our university so far had more than 150 PhD students, and we had already established more than 20 crores of research facilities, more than 20 crores, and we had, that is from university funded. Apart from that, our faculty members, we have able to get almost 15 crores of government DST funding in several programs like CRG, SRG, all those things. So we have a strong research program going on, and my office is somewhere here, and we have labs in the opposite building. So whenever you are coming to this site, once this pandemic goes away, certainly you can send me a mail or ring me. We'll be happy to host you. Professor Singh and my colleagues from Burhanpur College, I have been asking Dr. Rajibda for a long time to visit us. Hopefully, when this pandemic goes, be able to, we can see and we can physically, meet each other. So, time being, I'm going to discuss very briefly about our work that we have been doing, perovskite semiconductor nanocrystals. I'm going to show some of their synthesis. The issue is in perovskite, that how to make them stable, because these materials are uniquely important, and this has been widely applicable in solar cell and LED devices, but I'm going to focus on LED application that we are working here. As you can see that my background I did PhD in Singapore, from there until my postdocs, we have been working in colloidal semiconductor nanocrystals and study their operating devices. So when I joined as an independent faculty here, currently I have 4 PhD students working under me, and we have started working in the direction of semiconductor nanocrystals and therefore device applications. So as you can see the title, that perovskite semiconductor nanocrystals. So first question is, and for LED applications. So the questions comes that why semiconductor in electronic devices? Okay, so that's like to brief you, give you motivations to the undergrad students. You can see here that in the slides, that all of you are aware of this band alignment of the metal semiconductor insulator. The reason we chose semiconductor, because you can see that this is the material that we can control their electrical conductivity. We do not have scope to control electrical conductivity in case of metal, because it's a valence band and conduction band, they're overlapping each other, right? On the other hand, the insulator, there is no use, because whatever trick you can do, they can't make it to conductor, right? But the semiconductor, in normal condition, they are not conductor. But if you have some external forces, it can be electrical forces, it could be magnetic forces, it could be photochemical source or UV light, photon source, it can increase your conductivity. So that's how the transistor, that's the main of all these electronic devices, is acting as a switch, because the semiconductor, we can control the conductivity. That's the reason the semiconductor is the main material behind all these electronic devices. So I try to connect my talk that why the semiconductor. Okay, then the second question comes from my title, why the semiconductor nanocrystals? In the previous slide, I give you motivations that why semiconductor are good for these devices. Now, thing is, I'm not talking about semiconductor bulk material that I can see. I'm talking about material that can be made in the nanoscale. So that's called semiconductor nanocrystals. As Professor Singh has shown, some of those organic nanoparticles, 10 to 20 nanometer. And I think in today's concept, all of you know what is nanoparticle. I mean the undergraduate students. So you can see these are very tiny particle. I'm going to show you some of the image, how tiny these are. So why we use the semiconductor nanocrystals? Instead of bulk material, bulk means the macroscopic material, which we can see with the naked eyes, right? Why not we are using bulk? Why are we using the nanocrystals? So far we are using bulk. There are many, all those electronic gadgets are made of semiconductor, the bulk semiconductor. Now slowly, the nanocrystals, semiconductor nanocrystals are taking over it. And particularly I'm going to talk about the light emitting applications. The reason behind, I listed down the 4 points, but I have also shown that it's written here, the solution process electroluminescent display, that means LED displays, solution process, because this material, as we are chemists in chemistry lab, we can make this material in tons and kg scale, and this process is very cheap compared to all those technology, high pressure, high temperature, and like that, we can make this material in a very cheap, which is very important. And then these material-based devices are shown in the next generation displays. They are high in efficiency, white color gamut, low turn-on voltage, and low manufacturing cost, which is I mentioned in the beginning. Now, all of you might heard of QD LED TV, isn't it? QD LED TV. You might seen that this ad is going on in somewhere, or you might have visited some of the airports in the lobbies, either Hyderabad, Bengaluru. You can see these TVs are on displays. So these are QD LED TV. This is the same television I'm talking about. QD means quantum dot, which is another name of semiconductor nanocrystals. So these nanoparticles are embodied on this television screen, and you are able to see very pure color. That's the beauty of this material, that give you a very close to natural color. It's very difficult to mimic 100% natural things, but semiconductor nanocrystals is the recent technology that's showing or giving us a opportunity to almost close to nature, that exactly pure color, we are able to get LED televisions, displays, and all those things. Now, so we have given enough motivation why this using this. Now, what is the reasons why these semiconductor nanocrystals are so unique that we can use for either I said solar cell and LED? The main underlying fact is the quantum confinement, which is, again, all of you have gone through this quantum confinement, in one-dimensional box, particularly in 1D box. I think you guys have studied in your physical chemistry courses. So where you can see, this is a bulk material. When it goes to the nanoscales, what happened? The energy level got splitted, right? So that's called quantum confinement. Okay. Now this bulk material is a semiconductor. There's a band gap. So the band gap increases, right? And then also the continuum bands in this, valence band and conduction band, they got splitted. Okay. And that's called exciton. That means the electron goes from the ground state to the excited state. A bound state electron and hole, that means an electron hole together is called exciton, right? And how do you understand it? Again, is a simple physics, particle in a box model just now I mentioned. So that means this material source, this nanoscale material source, very interesting size dependent property. The same material, if you changes the size, it will give you the beautiful, you can see the interesting intense fluorescence across the visible spectrum. In this image, which is taken from our own lab, we are able to synthesize cadmium selenide zinc sulfide based nanocrystals that we are able to tune their emissions in order to changing. If you change their sizes, we are able to get the different colors starting from ultraviolet to blue, then green, yellow, orange, and red. And they are highly emissive. So this is the fluorescence image I'm talking about. This is under solution in toluene, and I shine through under UV light, and they give beautiful color for emissions. Okay. So that's the fundamental property why these semiconductor nanocrystals are very interesting. So we have understood the quantum confinement. Now, my understanding all these years why these semiconductor nanocrystals are so useful and different applications. In these slides, I'm going to show you what are the different applications we can make out from this material. Assume this is your semiconductor nanocrystals, which is around 10 to 15 nanometer size. I'm hitting it with a photon. If you hit with the photon, as you know, this is semiconductor, it has a band gap. So ground state electron will goes from the ground state to excited state, and that called exciton. This electron and hole is nothing else. The positive charge or the vacant electron state is called the hole. So these electron held together is called, what is called exciton. Now, what will happen? If you're able to separate this electron hole, you can make out different applications like photovoltaic, photodetector, and photocatalysis. This is one of the interesting facts of this material. Now, these exciton has a definite lifetime. Okay, how do you measure this? Through fluorescence spectroscopy, through fluorescent right-time measurement setup, right? So what is this lifetime? Lifetime is something I am to correlate you. We are having this seminar, okay, and we have said that it is 2 hours program. So if you go beyond 2 hours, 3 hours, you guys are going to lose your patience. So that means you have a patience of 2 to 3 hours to sit down. Honestly speaking, we have patience only a few minutes to listen something, but I'm just giving an example, right? Similarly, when this electron goes up, it has only some nanoseconds time scale that it can go and stay in the upstairs. Something you can think of, that electron goes from the ground cell, ground room, on your ground floor room to first floor room. Now it has some time limit, okay. After a few nanoseconds, due to the Coulombic interaction between this electron hole, the electron will come down. But before it comes down, if you make them separate, that is the solar cell, that is the photocatalyst, that is photodetector, okay. Now if you don't able to separate them, they will combine and we get a photon out, that is the fluorescence that I have shown in the previous slide, okay. Now, on the other hand, instead of photon, if we apply bias, electron and hole, they will recombine each other. We get a photon out, and that is called LED. So that's what I'm talking about today. So that's the things that in the same semiconductor nanocrystals, how you play with this exciton, the excited electron and hole, we can make out several applications. So I hope you understood that why semiconductor for optoelectronic devices, why semiconductor nanoscale material for optoelectronic devices, why it is so important because of quantum confinement. Now let us see the very basic layman understanding of LED devices. You can see this is the structure of LED, and this is a real LED. This is displayed in the in the lab, proof of concept, and this is the real LEDs. Now the LEDs are very cheap, easily available in the market. In in our Diwali times, in our Christmas times, we have decorated our homes with these small LED lights. So this is our very much affordable, and it is so easy to it is everyone's hand. Everyone is very cheap. 50 rupees you can spend, you can get in a 10-meter long LED small tuny lamps. So how the construction of these LED devices, if you see, so this is the material, the red color balls in between. So that's the material responsible for giving us light. So if you put a material that can give a red light, it will be red LED. If you put a material that can give you blue light, it will be blue LED. If you put a material that will be green light, it will give a green LED. If you put a material that will give a yellow light, it will be yellow LED. So like that. And there are some like a electron hole transporting injecting layer, hole injecting layer, and there are 2 electrodes when you're putting this electron hole, and then when you apply the bias, the light is coming. You can see from this top image. So that's the basic fundamentals. The actual is very complicated. We have to play many things, but I just want to give you from the layman perspective. Okay. Now, so we understand almost everything. Now, my question is, now next understanding is, how you make this nanoparticle in the laboratory. I think this must be very interesting for all chemistry students, isn't it? So what I often say, chemistry is like a cooking, is a cooking chemistry, you know. Then you might say that your mom may be best chemist. Yeah, it's true. Your mom or my mom, your wives, those are married, you know, my wives, they are wonderful chemists. I often told my, wife, you do to the chemistry, go to the lab, you do much more wonder than me. It's true. Because it is, they knows, okay, just give me, pardon me, I don't want to be gender biased. And nowadays, the boys are a wonderful cook also. So just, just don't take it otherwise. It is no longer the cooking is job for women, the today's world, we have moved forward. As Professor Singh has said, that year by year, the girl student enrollment is increasing. That's the hope, hope of, ray of hope that we are slowly reaching to the society. There is no discrimination based on sex, right? So that's a wonderful thing. So just want to try to connect the cooking in the chemistry and the colloidal chemistry. So as you cook in home, and we make a rice, if you make a rice, you put a water, if you rice grain and heat it. That's the chemistry, right? Same thing. We cook it instead of water, sometime in water, some solvent. We heat it instead of oven, we heating metal, and we cook it for certain time, and we got the nanoparticle. So that's how the nanoparticle is got. So I think you got an overall picture what is about, why the semiconductor nanocrystals, how do you make it, why they're good for the display applications. Now let us see the perovskite nanocrystals. Perovskite again is a crystal structure. You might heard of your crystalline semiconductor or solid state, your studies, right? Solid state chemistry. Calcium titanate is the classic example. But they have organic inorganic hybrid or pure inorganic cesium lead halide. So these materials are flourishing area of research because of their several applications like solar cell, LEDs, and all. Now you can see very recently, Professor Kovalenko in Zurich, they have invented a colloidal synthesis process of this material. So we can able to make this material across visible range, starting from blue all the way to red. And this is the fluorescence emissions we have taken in our lab. And then you can see we can make this material and we can change their band gap with the halide content. You may be, I'm not going too technical. I'm just giving you an understanding. Cesium lead halide is very, very unique material. It can absorb light and it can give a narrow emission. That's what we're looking for LED application. We need a very narrow color pure emission. Okay. So briefly, another few slides I have that what we're going to see today. This perovskite is very interesting, very wonderful material. But the challenges we're facing, can you make this material ambient stable? So that's the current challenge the community of this research community is facing of perovskite nanocrystals. They are not stable. So can you make them in ambient conditions? So far we are making them in an inert condition. Can you make them very stable? And can you make them from optoelectronic devices? There are some of the literature that we have recently published in 2020-21, a bunch of work we have published very recently. So this is for your reference. Those are interested, they can certainly, you can email me, or I can share the PDF copy of this paper where we have a detailed understanding of this material starting from synthesis to devices. Now our first challenge was make them in open atmospheric conditions. So we did make it, and you see this is the TM images, the tiny particle around 10 nanometer. They have highly crystalline in nature and then highly fluorescence, giving high, very good fluorescence. The fluorescence quantum will goes up to 70%. Okay, you can see this is ambient condition. The yellow light under UV radiations get very bright green, and this is the absorbance and emission. So it is the black is the absorbance spectra. It absorbs very, wide absorbance and very narrow emission. That makes this material interesting for display LED application. We need material. We have a very, very narrow color pure emissions. Okay. So what are the challenges? As I said, the stability is challenges. So our lab is focusing to find out a novel synthesis protocols that can overcome some of these stability challenges. And we have introduced an amine-free synthesis. Amine is a surfactant that we have been used, but we found that the amine is creating problem for the long-term stability of this material. So one of our nanoscale paper and chemistry European journal paper that's published in last year, we have shown that how this material can be made very stable for longer time if you make in the amine-free environment. Okay. Then study their stability. That my second question point was, can you make them stable? We study their stability long. So this is also this amine-free routes of synthesis. You can see we have very highly monodispersed nanoparticles. This is a crystal structure, absorbance, and then study is their stability. which studies the stability in ambient. You can see we have studied for more than 4 months. Our amine-free systems are very stable. This is our fluorescence quantum L. These are fluorescence images and fluorescence spectra, right? And then we have also studied under UV light, because when you want to use these nanoparticular devices, you need to be stable in different conditions. So UV light means it's a very harsh condition. So they say without amine, with amine the nanoparticle degraded very fast, but with amine they're very much stable, right? And finally, we make them a down converted LED. That's the down converted LED we fabricate in our laboratory. The green emitting LED you can see. So furthermore, in order to enhance this material, we have been looking for innovations, innovative ways to synthesize them, introducing new surface ligand. Here is one of this example. We can enhance their photoluminescence property from near unity in case of cesium lead bromide and cesium lead iodide. And finally, we tested the stability in ambient for more than 1 year. And also we can demonstrate the electroluminescence LED. And you can see this is a green element LED, this is a blue LED, this is yellow, and this is red, right? So that's how we're able to demonstrate. So you can see overall, in summary, I've given a understanding that why semiconductor, perovskite semiconductor nanocrystal is very good and useful for LED devices. We started what is semiconductor, why is semiconductor useful, what is semiconductor nanocrystals is going to useful, how to make synthesize it is through the colloidal chemistry, through cooking chemistry, how we can make them stable. We have invented different ways, and then finally we have utilized them to make them LED. I didn't go very much in scientific details since it's mainly meant for undergraduate students. Certainly, those any one of you are interested, you can write to me. You can get my contact or email ID from Dr. Rajiv Pramanik, and I can happy to discuss. This is my 3 PhD students, all the work done by them. Recently, one more student has joined. He's not there in the picture. And I'm thankful for the DST SARB and SRMAP for this funding. And I'm thanks to all of you for your attention. I'll be happy to have, you have any questions. Thank you so much. Over to you, Dr. Iqbal.
Thank you very much, Dr. Mishra, for such a nice, energetic, and enthusiastic presentation. Now the session is open for the discussion. If anybody have any question or query, they can directly interact with the, Professor Mishra.
Iqbal.
Yes, sir.
So can I go? Can I
yes,
ask?
Sir, sure,
Okay.
sure.
Nimai Mishra.
Yes, sir.
Wonderful talk.
Thank you, sir.
Enjoyed a lot.
Thank you so much, sir.
Okay. So you made all these nanocrystals wonderful. And the colors are excellent. So where you are really focusing to use them?
So we are focusing in 2 things, sir. As of now, as I mentioned, display application, LED devices, and as well as photocatalysis. I have not shown. We have another direction of work going on where we publish recently 3 papers. We are using them for organic photocatalysis.
Oh, organic photocatalysis. Very nice. Very nice. Can you throw some light about their EV? Like their excited state energy and all these things for photocatalysis?
So, sir, this is actually for organic photocatalysis, what we are studying here. We first take a model system to study the charge transfer process. That's the first thing we are doing now. So this organic photocatalysis for this material, it is actually very new. People have started with 2018-19. There are a few literatures coming up. So you want to know the band gaps or bands. So exactly, the band gap is in the blue, and in the green we can tune them, but exactly number is not coming to my head. But if you have any molecules which is you want to use for this material I can dig out and I can send you, sir, because there are recently few articles are there, and we have also seen the cyclic voltammetry. We have also located their conduction and valence bands, right? So, so I can see the band gaps, which is blue. In the blue, it is around more than 2 electron volts, right? So slowly it goes to 1 point something in case of red. But I think you were asking the exactly number of these electron volts, which is, I think, I need to check and I can send you.
Okay.
And,
Okay. Thank you, Nimai. One more quick question.
Yes,
Nimai, is there anything like 2-photon based nanocrystals? Any idea?
So in this case, 2-photon absorbance that is there, right? This upconversion materials is there, sir.
Okay,
Like,
sir. Okay,
yeah,
okay.
yeah. So particularly in this our material, there is no like this 2-photon, yeah, these things.
Okay. Thank you, Nimai. Thank you,
Sir.
Iqbal.
Thank you.
Thank you very much, sir. Sir, I have a question. Sir, when you are adding organic compound like thalamide type of thing into the cesium lead bromide
Yeah,
crystal,
yeah, yeah.
it's changing some property or it's helping. So how it works? So that's
So
what is the
basically,
chemistry?
basically, as you said, the thalamide, which is our second nanoscale we published in 2021, where we shown the thalamide is a novel ligand, which is able to, because this material, not only this material, it is a problem for any of the nanomaterial. The surface are vulnerable for oxidations, right? The surface are very highly energetic in nature, and there are very unsatisfied valencies on the surface. So we have introduced initial ligands, but ligands also not very much stable. They always have an on and off, okay? And the thalamide, we have used an extra surface passivator ligands, and they go and strongly bound to the lead of the cesium lead bromide and makes them stable. So they do not degrade very fast, okay? So that's how it is. We have done XPS studies, we have done the Peptide studies in order to validate our hypothesis, and we saw that yes, does thalamide goes and binding to the surface atoms, and the energies are changes for lead, lead energies are changes, and so we can able to able to restrict the dynamic nature. So dynamic nature of binding ligands actually pull out the surface atoms and eventually nanoparticle degrade. This is a common phenomena of any nanoparticles, and is more prone in this case cesium lead bromide perovskite because they are highly ionic in nature. They try to degrade very fast. So that's the key challenges. Otherwise, these material going to replace, by the way, in the near future, all the solar panels, because they have shown more than 30-40 efficiency already is there. Only issue is this, the stability. The moment Michael Gadgel is working in, Henry Smith is working that. So if they found, and all of us community found the solution, it is going to revolutionize the solar energy sector.
Sir, there is a few questions in chat box. Due to lack of time, I will take one or two.
Sure.
So
sure.
one of our students asked, except LED, what are the application of nanocrystal?
Hello?
Sir, may I audible?
Yeah, tell me.
Yes. So one of our students asked, except LED, what are the application of nanocrystals?
It depends several applications we can do for, as I mentioned beginning. If we play the exciton, we can make solar cell, just now I mentioned, we can make photodetector, we can use them as a photocatalyst. We also can use as a biomarker, because these are fluorescence nanoparticle. We can level with them, tag with them some of the biomolecules, and we can see the imaging, bioimaging, to track many diseases. We can track specifically you can track the tumor. The semiconductor nanocrystals has been widely used in mice in cancer detections, and it's very, very successful. The human trial is only prevented because this cadmium is toxic. People have been working low toxic materials, less toxic material, and so there's several like biology to physics devices. There are several applications of these materials.
Thank you.
Thank you. You are muted. I think yourself.
Thank you very much once again.
Thank you so much
for your valuable time with us, and hope to see you again in the future.
Sure, definitely. My hometown is nearby to Baharampur. Whenever I'll go, I'll try to visit. I'm from Katoa, so just 2 hours from there. Love to go. I told Rajiv Da when I come, we'll go, and hopefully situation will be better.
Please come to visit our department, sir.
Sure, definitely.
For us.
Okay. Definitely.
Thank you.
Okay. Thank you so much. Thank you. Bye. So I'll leave in between. We have another meeting at 4 p.m. I'll be here for some time.
Okay, sir.
Okay. Thank you.
So we'll move to our next speaker. So already he has joined. So our next speaker, that is last speaker of this technical session, is Dr. Pavel Banerjee. May I audible, Dr. Pavel?
Yeah. Am I audible?
Okay. Yes, very much. So he's postdoctoral researcher, University of Copenhagen, Denmark. Dr. Banerjee has finished his BSc degree in chemistry from Viswabharati University in 2013. Then he did his master's in physical chemistry specialization from same university. And after that, He has obtained his PhD degree from Indian Institute of Technology, Kharagpur in 2021 under the supervision of Dr. Nirmali Sarkar in the field of experimental physical chemistry. His research interest in the field of physical chemistry, dynamics of biological building block, molecules and their membrane behavior using different fluorescence microscopy and spectroscopy. Dr. Banerjee has published his research work in many reputed international journals with a high impact factor. With this short introduction, now I am requesting Dr. Banerjee to start your today's talk. Dr. Banerjee, the virtual mic is up to you now.
Thank you for your introduction. I just try to share my screen. Is it? Can you see my screen?
Not yet. It's coming. It's coming.
Yeah. Now.
Yes. Now it's visible. Please make it in the slideshow.
Yeah, I make it now.
Probably it's coming.
Is it in slideshow now?
No, it's stuck. It is not moving.
Should I share
please close it and again reopen it.
Maybe I see the total screen. Yeah, now you just tell me.
Yes. Now it's fine. Yeah.
Okay. First of all, thank you. Hi, is it okay?
Yes, it's fine. It's okay.
Yeah. Hi. First of all, thank you, Dr. Iqbal, for introducing me, and thank you the organizing committee for inviting me to giving a lecture. Thank you for the total organizing committee. I don't know everybody, but thank you the principal. He has sent me the mail, and thank you Rajiv Da. Rajiv Da is my lab senior. He has invited me to giving that talk, and thank you Professor Indi Pradip Singh, and thank you Professor Nimai Misra for his wonderful talk, wonderful introduction of this seminar. And they have shown the application of fluorescence spectroscopy and microscopy in the field of generation new novel materials and the applications of those novel materials. So in my case, my research interest on most of focused on biophysics. So I am also telling about some novel material or some biology, but that mainly focus on novel biomaterial type of things, not nanomaterials. So yeah, and I have tried my best to structure the presentation in simple manner, because I know I when I was doing my BSc, my undergraduate in Viswabharati, sometimes I see like professors or lecturers come from outside, as Viswabharati is a central university. Many people came there to deliver the lectures, but sometimes the students, undergrads can't understand anything. So I have tried my best to structure the presentation as simple as possible, mainly focuses on the general things. So yeah, if any questions you have after the presentation, you can ask me. Yeah, so my presentation is, the title of my presentation is Change in Bilayer Properties, a Mysterious Avenue Towards Origin of Life. So there are many terms. So I am going to discuss about the how step by step. So in my title, you see many terms maybe you don't know or you are not familiar with. First of all, what is bilayer? I say something about bilayer properties. So I will discuss about what is bilayer. Then again, I say a term that is called origin of life. So I will also uncover that things, that what is the concept of origin of life. And then I again use the term that is mysterious avenue. So that is also that also may look peculiar. Why I say that's a mysterious avenue. And then I will discuss about some of my work, some of my experiments and results, and then I will conclude, obviously, my results or my works. And you say the writer and philosopher Alfred R. Orange, he said that nature is the objective creditor of every living being. So whatever I will discuss here or whatever I will show here, that is based on science and science or natural science. So in the origin of life, I am not discussing anything about like God created us or that type of thing, religious thing. So that may be a concept, obviously, but in my presentation, the only focus is in the understanding the science, natural science behind that origin of life or that type of things. So first of all, you know the biomolecules are mainly divided in 4 parts. The mainly 4 parts are carbohydrates, but the biomolecules get energy from. Carbohydrates mean such as sugars. Sugars is glucose, fructose. This is high school chemistry. You all know the name of these things. And we take carbohydrates from rice, from potatoes, this type of things. And then lipids. Biomolecule stores energy in lipids. And lipids are there are saturated fat, unsaturated fat. And I am only focusing on phospholipids. Why? Because phospholipids can form membrane. I will show you how phospholipids can form membrane, and how are these things. So these are the lipids, is one of the parts. And again, biomolecule builds cell with proteins, and the smallest structural unit of the protein is amino acids. So we all know amino acids. We have 20 very special amino acids for us, like glycine, alanine, all these things. And again, another important part, this is biomolecules builds genetic code with nucleic acids that made of nucleotide, and nucleotide also made containing nucleobases and pentose sugar. So nucleobases, you all know that like RNA bases and DNA bases, like uracil, adenine, thymine, those type of things. So those 4 are the main pillars of biomolecules we have. So now you see what are the forces? What are the forces that make that type of large biomolecules? So one of my interest in the PhD is based on that self-assembly of the small biomolecules. And my approach was mainly bottom-up approach. So what is bottom-up approach? Bottom-up approach means small biomolecules, single unit of biomolecules, they self-assemble with each other using some forces spontaneously and make that type of big structures. So what are the forces? The driving forces are mainly these 3. There are many others, but mainly are these 3. First of all, electrostatic interaction, electrostatic repulsion, maybe electrostatic attraction. Another one is pi stacking. So when the molecules have pi bonds, and that many biomolecules have pi bonds. And what are the pi bonds there? There are many kind of pi interactions. That's the another kind of main interaction in the things. Again, the hydrogen bonding interaction. This is also a very important interaction. Like we know, hydrogen bond donor, hydrogen bond acceptor, the molecules, electron affinity, electronegativity. So this is a hydrogen bonding interaction. That's also an important thing. So now I saw a funny picture. Yeah, I think you can see that. And we all read this Gulliver Travels in our childhood times. So why I saw this picture? You see, the small people here, they can tie up a big people like Gulliver Travels in the nano world. How? Because when these forces are actually very small, if we compare with the covalent forces, covalent bond forming forces, these forces are very small compared to that covalent bond formation forces. But when these forces combine like these small peoples, they can tie up like big people like Gulliver Travels. So they can form large biomolecule structure like this. So these are small forces, but when unity we stand, obviously, they can form this type of large biomolecules. So you see, I start from the very ancient world where there are only elements like carbon, phosphorus, oxygen, hydrogen, nitrogen, and then they combine to form, first of all, some compounds like carbon monoxide, nitrogen, carbon dioxide, water, hydrogen, like this. These compounds are formed. And then again, they are going for, again, many complex compounds. Like you see, these molecules go together, some chemical reaction happens. How the chemical reaction happens, we are still, now we can produce in the laboratory that type of molecule. But we don't know how in the ancient world, when there was no laboratory, how nature produces this type of thing. Scientists are on it. We have some answers. We haven't some answers. We don't have most of the answers actually. So now these molecules can combine to form complex structures like formaldehyde, HCN, ammonia. And you see, these molecules then combine each other to form the main things of the life is phospholipids. Phospholipids, these are the one kind of lipid which has hydrophilic part as well as hydrophobic part. And as they have both hydrophilic part and hydrophobic part, they can self-assemble to form this type of beautiful structures. These molecules, this head group are hydrophilic part, mainly this one. And this tail group is the hydrophobic part, so this one. They can assemble like these beautiful structures. They can form these beautiful structures which called lipid membrane, and which give us like a concept of compartmentalization, like a room. And then the nucleobases can form DNA and RNA, and the amino acids are the unit of the protein. They can form protein structures. So when these three things like compartmentalization, replication, and metabolism, when these three things combined, and that is the beginning of the life. So this is the form of earliest life actually. So there are many things we don't know how this reaction happened in the ancient world. There was no laboratory, there was no scientist, there was no human. So how these things happen, how nitrogen and hydrogen mix together and they form ammonia, how these phospholipids growing on. So this is another field of research in today's community. People, we are very much interested about it, how life begins in this world in a scientific way. So there are many theories. The most important, or many 7 theories are there. Scientists are telling that there may be an electric spark. That electric spark gives the energy of that type of reaction between the elements, which can form a complex compound and then some complex things. We don't know about that. Maybe the electric spark was the motivation. Some scientists claim that molecules met on clay, a kind of special clay in some subcontinent area. The molecules are reacting only in that specific condition. Some scientists say sea, deep sea. Sea is the place where the life begins. Some people say life has a chilly start, like -40 degree, -60 degree. Life has started from that type of temperature, that type of certain environment. Again, some people say if we can understand how DNA forms, then we can know how life began. But yeah, we are processing it each aspect. Now we know in many things about DNA. How this is a very big field, very wide field of research. G quadruplex, DNA formation, the biophysics of DNA, protein. So this is a very, very promising and ongoing field in the scientific community. Then some people say no, not DNA. First, maybe life starts from very small things, very small molecules. They self-assemble. Actually, my research on this particular field, like self-assembly of small molecules, we believe that maybe life has a simple start than we think. And yeah, obviously, some researchers would say alien. There are people, there are animals, there are humans from another planet. They come here, they put life here, they put molecules here. So we cannot omit anything. Maybe God also a alien. We don't know. So if we look at the time frame, the Earth formation has happened 4.5 billion years ago, and we are actually discussing in this prebiotic chemistry. This is 4 billion years ago, where many molecules were there. We are certain from different sample testing, because the techniques all the techniques are actually we are developing in techniques, scientific techniques, scientific instruments. So now we can analyze many things, and we have analyzed, and we are sure that there are in that particular time of the time frame of the Earth, there are that type of molecules. But then we can separate that. After that, we have pre-RNA world, then RNA world, then the DNA world, and then life starts. So I am not going details of that. We are actually focusing in that thing, prebiotic chemistry, like the earlier, only this phospholipids, these nucleobases are present there. But we don't know how they react. We don't know exact condition, how they're going to form life. So we are mainly scientists, or we are interested to use the phospholipid vesicle membrane, not using cell. People are using cell also, because techniques are improving. Now people can monitor cell. But you see this is a particular cell, and you see in the cell is a very complex structure. There are many organelles in there, Golgi bodies, mitochondria. So when you monitor the dynamics in a cell, this is very difficult to monitor the whole cell. You can monitor one particular organelles, like you can monitor mitochondria, you can monitor nucleus, you can monitor Golgi bodies, but it's difficult to monitor as all over thing. So people then, that's why people use the phospholipids. The phospholipids actually, phospholipid membrane, actually this is the bilayer. Phospholipid membrane actually successfully mimic the cell things, but this bilayer is mimicking that cell membrane, which is hydrophobic in nature, and this is the water pool, this is hydrophilic in nature. This is these are the mimicking things. So so we can understand more things than monitoring the whole cell at a time. So now my thing is generation of vesicles, or generation of these new vesicles from a particular things. So this field is going on from 30 years ago. First, Peter Luisi published a chart. He also got Nobel actually. So this is the thing. You see, this is a single vesicle, and after the single vesicle, they have showed in their paper, in their manuscript, 2 certain pathways for self-reproduction. What is self-reproduction? We know what is reproduction. Self-reproduction means vesicles are generating from a particular vesicle. Like you start from this vesicle, and we applied some external forces, not mechanical forces, some external chemical. Here in this step, you see the vesicle grow larger from smaller. They need actually form a different structure. This is called vesicle buds. So these are the vesicle buds, and then they give birth of a small vesicle. So we can call this vesicle, the new vesicle, as a daughter vesicle, and this primary vesicle, which is the starting point, that vesicle as a mother vesicle. So there are different mechanisms, but that research actually for 20 years, that research only limited to fatty acid vesicles. But recently, after 2010, there are many papers coming out, not many actually, some papers coming out that not only fatty acid vesicles, also phospholipid vesicles, because fatty acid, and when you compare fatty acid vesicle and phospholipid vesicle, obviously phospholipid is a more complex thing, and phospholipid vesicle is a more strong vesicle. So people didn't observe any kind of self-reproduction from phospholipid vesicle behind that time using this simple optical microscope technique. But now the techniques are improving. Now we are going through super resolution actually, where this means like we can go beyond the boundaries. We can monitor more smaller things. We can monitor in more deep things. And because of this type of improving techniques, now we can see that phospholipid vesicles also can give birth of small vesicles, and this is also a very growing field now. So now in my study, I am actually monitoring. I have actually monitored the interaction of a peptide. That particular class of peptide called cell-penetrating peptide. So what is cell-penetrating peptide? You see, this is the peptide. This is actually now, you know, I have already showed, this is the bilayer. This is the vesicle growth, the vesicle division, the vesicle buds. But now I am introducing another term. This is peptide, cell-penetrating peptide. We all know peptide. Peptide is combination of some amino acids. So cell-penetrating peptides mainly are arginine-rich peptide. I have used a nona-arginine peptide. Nona-arginine means 9 arginine moieties are combined together here. So these peptides are special type of peptides. Why they are special? Because they can uptake, they can deliver cargoes like medicines. They can deliver that type of things inside the cell. So why I am saying this? Because delivery inside the cell is not easy. Because you see there is a hydrophobic bilayer. And for this hydrophobic bilayer, most of the things are impermeable to the membrane. Ions like sodium, potassium, calcium, they cannot move, they cannot permeable to membrane. They cannot go through the membrane because this is hydrophobic, and that sodium, potassium, calcium, they are charged species. So these charged species cannot go to the inside the cell. So we need something to pass it out. And cell-penetrating peptide is that kind of vehicle. You can say this is a vehicle. This load that type of charged things, and they can readily permeable to the membrane, and they can deliver the cargo, and they can, again, they are not affected by the membrane. They are not affected by the inside of the cell. They can deliver the cargo like a vehicle, and then they again back from the cell to the extracellular spaces. So these are the cell-penetrating peptides actually. So why we need cell-penetrating peptides for this? Because in the present world, antibiotics resistance is a very worrying things actually. At present, according to the scientists, 80% of antibiotics are useless because our body, our human body, resists to that antibiotics. So that antibiotics are not in use, like which are very usable before 10 years. That antibiotics are not in use now. So this is the alternative pathway to using peptide, using this type of protein for a alternative approach of drugs, alternative approach of drug delivery. So that type of system, and this is in very interesting and very growing field. In 2018, the 3 renowned scientists got Nobel Prize for researching in that particular field. They have used the proteins and peptides and enzymes as the alternative kind of drug. So they have won the Nobel Prize in field is now. Already Professor Mishra and Professor N.D. Pradeep Singh, they have introduced what is fluorescence, what are the things it affects, how it is going on. So I have just taken 2 presentations. I acknowledge Professor Shobham Sen. He is the professor from JNU, and when I attend one of his class in a conference, I found this too fascinated, this presentation. This is made by him actually. I just want to present this to the undergraduate student. I hope you will enjoy it and you can clearly understand what is the fluorescence and what kind of thing it affects the fluorescence. You see, so these are the molecules in the ground state. So S0 is ground state, S1 is excited state. So these are the molecules in the ground state. So after some time, there is photon. Photon is excited the molecules to the excited state, and there is some certain frequency and there is a certain time scale. After that, you see there is a less polar state for the excited state, and this molecule move to the less polar state. This is called environmental or solvent relaxation. And after that, this from the less polar state, this comes to the ground state, and this is fluorescence actually. This is fluorescence. This is non-radiative emission, and you see this is we can get due to that emission, we can get an emission spectra in a fluorescence spectrophotometer. And if we go to more polar things, you see we can get again emission, but now this is a different time scale, different frequency, and we can have different wavelength. So there is a rate shift, and rate shift means we are going to more polar things, more polar solvent or more polar environment. So we can just clearly see that type of things using the fluorimeter only, the steady state fluorimeter. So when we get to time resolved fluorescence, what we see again, the molecules are there and molecules are going excited to the excited state, and then it go to the solvent relaxation. And but like Professor Mishra is saying, what is the time resolved thing? Like it depends. All molecules does not emit at the same time. They have different time scale. Like you see, This I show steady state spectra, but when you go to time resolved spectra, they are not emitting in the same time. The molecules are heterogeneous, and you see they are emitting like this one. First this, so this takes some time, and using time resolved spectra, we can monitor the fluorescence intensity in a time dependent manner. So that's I think that will very clearly illustrated in this presentation. So we need for this time resolved thing, we use many different instruments like upconversion, TCSPC. So that's the name of the instrument actually. Don't need to worry about that. So these are instruments I have used for my study. This is my microscope setup. This is the microscope film. This is called Fluorescence Lifetime Imaging Microscopy and Fluorescence Anisotropy Imaging. That two techniques I have used. And this is simplest diagram. So don't need to go, I am not going details of that. If anybody interested, I can go up to that. So this is just a microscope setting. Yeah. So now for my work, I am going to my work. So this work I have this is the size of the vesicle. So we have some instrument that is called dynamic light scattering, DLS instrument. We can measure the size of the vesicles. We have prepared some vesicles, the lipid bilayer vesicles, and we have measured the size. And then you see this is not homogeneous. There are different size of the vesicles. Then we can just use sonication. Sonication is a mechanical thing we can employ to that type of vesicles to make the size homogeneous. You see, we sonicate this type of biomaterials, this type of vesicles for 30 minutes, and we get a homogeneous distribution of vesicles. And what we did then after preparing the vesicles, we incorporate a fluorophore. The fluorophore is called DCM. So what is fluorophore? Fluorophore is the thing which actually give the informations of these assemblies. So this fluorophore is hydrophobic. We load this fluorophore in the vesicle in such a way that fluorophore go to the bilayer region, that the hydrophobic region. So that fluorophore will give us all the information which will happen in that bilayer part. And then we have added cell-penetrating peptide in that vesicle. And we see we have added in different concentration from 5 micromolar to 35 micromolar. We're using in a 5 micromolar step. And this is a steady state fluorescence spectra, steady state microscopy. And you see there is a certain increase in fluorescence intensity. So why this is increased, I will discuss it. But that increase means there's something happening in the bilayer when the peptide is going there. So we fitted that intensity. We have tried to fit that intensity. So there are certain rule. If this fitting is very good in the linear manner, then we can say there is a particular mechanism by which the peptide is going to the bilayer. So if it is not fitted well linearly, in our case it is not fitted well in linearly, rather it fitted very well in non-linear manner. So it actually reflects that there is not only one mechanism, there are many mechanisms. There are 2-3 mechanisms maybe actually happening when the peptide is going through the bilayer. So now we take a particular concentration. We take 30 micromolar concentration of peptide, and we have monitored in a time-dependent manner. Like we start from initially, and we have monitored up to 3 hours, 3 days actually, 72 hours, 3 days. And we see the intensity actually increases continuously with a rate shift. So we can say, I have shown in my presentation. So we can say the fluorophore is going to a more polar environment when the peptide is going on. So the peptide actually obviously perturbs the bilayer membrane. So this is DLS and this is zeta potential. So zeta potential means the electrostatic interaction. Zeta potential actually reflects the electrostatic interaction between the peptide and the membrane. We see there is a trend that the zeta potential and DLS, there is an increase in size and increase in electrostatic interaction, and after some point that actually decreases. So this effect is called actually matrix effect. So like increases, like vesicle bud forming, there is an increase in size, increase in interaction. Afterwards, it again come back to its like previous stage. So this is the images I can show you. So you see, this is the film images, fluorescence lifetime images, and these are the TEM images, like electron microscopy images. You see, this is the without any peptide. These are the vesicles. After 1 hour of adding the vesicles, you see there are different shapes. These type of shapes, there are lipid tubules, there are vesicle buds. I show you that type of structure in when we illustrate the things. So there are different shapes when we add the peptide in after 1 hour of addition of peptide. After 8 hours, this type of shapes are there with larger size, and after 72 hours, means after 3 days, there are very small type of vesicles. These are called Uni Lamellar Vesicles. You see, there are many small Uni Lamellar Vesicles. These are actually the daughter vesicles. And we can see monitoring the lifetime. This is the lifetime measurement from the images. We can, using the fluorescence microscopy, we can monitor the lifetime as well as the image. So when we analyze the lifetime, we see that when we add these 1 hour vesicles, actually have least lifetime. They have the least lifetime. And when we go to the 3-day vesicles, again the lifetime actually increases. So here the lifetime means the rigidity of the vesicles, because our dye is a hydrophobic dye and it is in the bilayer. So this decrease in lifetime means that dye is enjoying a less rigid environment. So we can say this is the least rigid structures, and we will prove it by other structures also. Again, we have taken 3 type of vesicles, 3 different size vesicles, and we continuously monitor. Time result be like 2 hour, 3 hour. We have monitored. Here we have showed for the test 8 minutes maybe. Yeah, 8 minutes. And we have monitored the path of the vesicles. These are the path of the vesicles. We have analyzed in the MATLAB. MATLAB is a software where you can analyze many things. And so we have analyzed the path of these vesicles. These are the path of the vesicles. You see, these are the path of this vesicle, number 1 vesicles, and this is a small vesicle. You see, it moves very fast from the coordinate from 160 to 240. When the largest vesicle, it moves only 373 to 374. So it reflects you that larger the vesicles, less the movement. So you can see from the microscope. And these are the actually mean square displacement curve. Mean square displacement curve is actually so what are the phenomenon of in the vesicles are happening during the time. So if there is no phenomenon, just only vesicles are moving here and there, so that should be these curves, mean square displacement curve should be linear with time, with a delay time. But you see that curves are not linear. That curves, there are many kind of kinks in the curves, and that kinks actually due to the production of the daughter vesicle, due to the production of the small vesicles. We also have video. We also have captured video that type of vesicles production. This and another type of imaging. This is anisotropy imaging. This, if I told you like in very short, in a very easy manner, this means this value is an anisotropy, fluorescence anisotropy value. So when this anisotropy value is high, it means that hydrophobic dye rotate, that hydrophobic dye actually using very good rigid environment. And when this is less, we can say this is very less rigid environment. So we see these are we can call initial vesicle. When there is no peptide, there is nothing. So this is initial vesicle when the anisotropy value is 0.3. But when we go to this 1 hour vesicle, you see in 1 hour vesicle, there are different type of lipid tubules, different type of lipid buds, and we can see the anisotropy value is 0.13. So it's a very, very drastic change. So these are the mother vesicles. These are called mother of the vesicles. And after 3 days, we have found daughter vesicles when these vesicles come from the mother vesicles. And we see again the rigidity of the bilayer actually increases going from mother to daughter. So we have characterized all the 3 type of vesicles. This is the initial vesicle, this is the mother vesicle, and this is the daughter vesicle. So my conclusion is, model lipid vesicle self-reproduce to generate unilamellar daughter vesicles in presence of a peptide. So this is a very new complete phenomenon. We have monitored, we have showed that peptide can do that type of self-reproduction. And fluorescence lifetime and anisotropy image exquisitely capture the change in the lipid bilayer rigidity. I have shown by different techniques. And our result all obviously gives some insight of peptide membrane interaction, as well as it can help to process or to progress the field of that origin of life, like phospholipid vesicle. This is a lipid vesicle that self reproduce, and this is the main process that how biomolecules reproduce itself. So that's the point to go to that path. This is very long path to discover the origin of life. Obviously, this is a very small contribution. Like, yeah, we can understand that presence of a protein actually give rise to self reproduction of a lipid things. So there are, in the ancient world, there are proteins, there are lipids. We don't know how life comes, how the things, but we can see when that particular type of proteins are there, that lipid vesicles self reproduce itself. So reproduction is the main thing to have the origin of life. So this is a kind of that type of approach. So we can say that, yeah, this is the vesicles without any peptide. This is the mother vesicles. When different shapes are there, you see there is illustration that these are the peptides, green ones. They can put the pressure on the membrane, and we can say that after 3 days, that the daughter vesicles, the peptide can insert and they can divide the bilayers, and there the formation of new bilayers also. So we can say self-penetrating peptide induces self-reproduction of phospholipid vesicles. So I again thank the organizing committee, Professor Nilmani Sarkar's lab. I have done this research in IIT Kharagpur actually. I will thank my family and friends. They are also important part of life. And this work I have published in ChemCom in 2018. If anybody interested more, you can contact me. You can go through the paper. So yeah, and I will conclude saying this, that this is a very emerging topic in biophysical research. We chemists have more potential to do these things rather than biologists actually, because this mainly governs by the chemical interaction. We know chemistry, we know chemical interactions, we know that type of non-covalent interaction. We can learn biology quickly actually. If we want to do, we know some kind of instrument. So we are the potential candidate actually for this parts of research. We can go beyond the biologist actually if we pursue with that type of research. So this is a very important part, and we actually know very little till date about the origin of life. But according to David Hilbert, that is the approach. We must know. We will know in a time. And obviously, you always know chemistry is try. So we can try. We will try our best. So we are I again say, we are the most potential candidate to pursue this type of research. Thank you again, everybody. And I am open for any question.
Thank you very much, Dr. Banerjee, for your nice presentation. Now the session is open for the discussion. If anybody have any question, they can come forward and directly interact with Dr. Banerjee. I have special request to all of our students. If they have any question, please ask. It will be great opportunity.
একটা কোশ্চেন পোস্ট করেছে, এটা একটু বলে দিলে ভালো হতো।
Okay, so one of our students had asked why we use fluorescence spectroscopy for the measurements of bilayer lipid property of a vesicle to understand origin of life.
Yeah. That's a good question. Thank you. We not only use fluorescence spectroscopy and microscopy, we use different techniques. Actually, there are different techniques, but nowadays we fluorescence spectroscopy. You see, in my presentation, that we can clearly have the different type of lifetime, different type of things we can explore from the images. So that can say that heterogeneity of the bilayer structure, we can detect the heterogeneity. You see the structures of the curve, there are heterogeneity. We can see the clear change in the spectra, in the fluorescence spectra. And actually, we are lucky that we have a range of white fluorophores. Like we can, and like Professor Mishra and Professor N.D. Pradeep Singh showed in that presentation, that many chemists, we are on the designing the nanoparticles as a fluorophore. We are designing nanoclusters as fluorophore. So we have that tools. We have that power to monitor the bilayer using fluorescence. So that's the actual limitation of fluorescence spectroscopy or microscopy, to have a proper fluorophore. So now we have that type of proper fluorophore. And why we using this thing to using origin of life? Like I say, that origin of life, we still don't know. We don't know where from origin of life comes. So this is only the things, like in my work, I have shown that there are interactions of protein and lipid. So I am start from that point when I assume that in the ancient world, protein already formed, lipid already formed, and vesicles already there. I assume that point. And then I see when that type of protein and that type of vesicles come together, come close together, and then that protein can form that type of initiation of self-reproduction, and we can monitor easily. We can see clearly using fluorescence microscopy, as well as you see different spectra of fluorescence spectroscopy. So that's a good technique, but that's not only one, that's not the only approach. There are many approaches. Electron microscopy approach are there, scattering approach are there. But our fluorescence community also, we are now growing. We are now stronger, becoming stronger for this type of research.
Okay, thank you.
I have one question.
Yeah.
So how much is the spatial and time resolution for your lifetime imaging and anisotropy imaging?
This is the limitation. Obviously, there is a limitation because in my lifetime imaging and anisotropy imaging, I have used TCSPC. So TCSPC is my system resolution is like 120 picosecond. So we can't measure below that because the film is actually that confocal microscopy, which is attached to the TCSPC. And as the TCSPC only can measure the picosecond time resolution, so my instrument or my facility restricted up to 120 picosecond time resolution.
And spatial resolution means how much? The spatial resolution means how much nanometer?
Like the the specialist, this is only confocal microscope, so we can only we can monitor only kind of 500 nanometer. So I hope if this type of research will conducted by the other advanced technique like super resolution, so then we can obviously can monitor directly the cell membrane, not only vesicle membrane. Yeah, my resolution is only 500 nanometer.
And for the anisotropy imaging, that data analysis, means your lab has wrote this code for the analysis, or you?
Yeah. For the anisotropy imaging, for the anisotropy imaging analysis, we wrote the code in the MATLAB. Yeah.
Okay, great. Thank you.
And I am for the undergraduate student, I just give a suggestion. Like in our time, that's not very much there. But if you can have any opportunity to learn any computational language like Python, like MATLAB, please do it. It is very important if you want to pursue not only science, not only PhD, in many parts of your life of your career. If you have any opportunity, please pursue any of the computational course like Python or MATLAB. It will help you.
Okay, thank you.
Okay, so if we don't have any question, let's thank Dr. Banerjee for his excellent presentation. Thank you once again for your valuable time with us, and hope to see you again in the future. Thank you. So
thank you, Dr. Obviously,
we are almost end of our today's program. So now I'll request Dr. Pramanik. Okay, sorry. Okay. So anybody have any question?
The question, how rigidity will be changed if we take a hydrophilic dye?
One of our students asked, sir, how rigidity will be changed if we take a hydrophilic dye?
Yeah, the good question. But the thing is, if we use hydrophilic dye, that time that time we are not monitoring the bilayer because bilayer is hydrophobic. So if we use hydrophilic dye, then we can monitor the inside lumen of the vesicle, where the water molecules, where the hydrophilic molecules are there. We can monitor that part, not the bilayer. But yeah, definitely that will also give us some new information, how the lumen changes. That will give us information. If we have any change, then we can say the peptide actually insert to the lumen. If there is no change, we can say, yeah, the peptide can't go to that lumen. So if we use hydrophilic dye, there may be less possibility to have more information because this lumen is, the peptide have to cross the bilayer to go to the lumen. But obviously, that will be another approach of the research. Thank you for your good question actually.
Rajibda, can I ask one question to Pavel?
Yeah.
Yes, Dr. Siddhartha, yes.
Nice, very informative talk, Pavel. I want to ask you one thing, not ask, rather I want to know one thing, that instead of a hydrophobic interactive dye or hydrophilic whatever, if we able to react some dye in the bilayer molecule, able to react, then the scenario and picture may be more clear to us, right or not? I want to know.
React means like you are saying like on off
just
blink.
tagging, reaction or tagging.
Yeah. So that's kind of dye loading actually is not a straightforward process. There are many kind of process that loading the dye in a particular region of the vesicles, particular bilayer, particular like outside the bilayer, inside lumen of the bilayer, or the lumen of in the hydrophilic part of the vesicle. So there are different types. Yeah, if we start with that type of lipid, which is actually conjugated previously from when we initiate the vesicle preparation, in my procedure, I first prepare the vesicles. Then using some procedures, that procedure is called Fritz-Thaw and extrusion, we have loaded the dye in the bilayer. But yeah, we can start with that type of thing, that type of fluorophore, which the fluorophore is conjugated to the lipid bilayer. Then we can make vesicles, and that will also we can compare the results. We can't say that will be better, but we can compare the results obviously. Thank you for your suggestion.
Thank you.
Thank you, Dr. Banerjee, once again for such a nice interactive session, and hope to see you and hope to learn you from in the future. Okay, thank you.
Thank you.
So now we are almost end of today's program. Now I'll request Dr. Pramanik, the coordinator of today's program, to summing up the session and propose vote of thanks. Dr. Pramanik, the virtual mic is up to you.
Okay, thank you, Iqbal. So my warm afternoon to you all. Honorable Speaker, respected President of Governing Body, Principal, worthy member of Bahrampur Girls College family, the dignitaries of other institute, valued viewers from different disciplines, and my all beloved students who are virtually gathered here today for the one-day national webinar on this interesting topic, organized by Department of Chemistry, Bahrampur Girls College, initiated by IQAC. It's my proud privilege to propose a vote of thanks for today's note and knowledge the contribution of those who work really hard to make this event happen. Also, I like to take this opportunity to record my heartfelt thanks for the all team members for the support and right guidance. Well, such an event cannot happen overnight. We'll start rolling around several months ago. It's required planning, a bird's-eye view for details. We have been fortunate enough to supported by a team of very motivated and dedicated colleagues from our college who knows their job and they are result-oriented. I cannot thank enough everyone for their participation and their willingness to complete tasks beyond their comfort zone. I like to express my heartfelt gratitude to Professor Mrinal Kanti Chakraborty, President, Governing Body, Bahrampur Girls College, for his wonderful inaugural talk, Dr. Hena Sinha, Principal of Bahrampur Girls College, for her excellent welcome address, Professor Subhashri Chakraborty, IC Coordinator, for her thoroughly introductory address. Sincerely, I want to thank all the faculty members of various departments who handled the event throughout. Finally, I would like to thank all of you present here for making the time to be with us and helping us make this event successful. On behalf of Department of Chemistry, Baharampur Girls College, I extend really hearty vote of thanks to our keynote speaker, Professor N.D. Pradeep Singh, who spared time with us from his busy schedule to grace the occasion. Today we had an opportunity to hear your thought, and this will surely going to encourage us in future events, as well as encourage our students to pursue science research as career and livelihood. We are all inspired by your great work. Thank you, Professor N.D. Pradeep Singh. I also express my really hearty of thanks to today's speaker, Dr. Nimai Misra, for his wonderful presentation on the topic of perovskite nanocrystal synthesis, stability, and application in light emitting diode. Dr. Nimai Misra talked about perovskite nanocrystals in details about the synthesis procedure, how to stabilize them. Then he studied some fundamental optical property, particularly the fluorescence and photoluminescence, and he explained quietly how to improve the property in order to apply this material in light emitting devices. He explains all this topic quite elaborately. So I really thankful to Nimai Misra coming here for your short notice. I wish also to express my gratitude to Dr. Pavel Banerjee for providing insightful information on the topic change in lipid bilayer properties, a mysterious avenue towards the light. Dr. Pavel Banerjee nicely presents the structure of the lipid bilayer and vesicles, which are mimic of cell membrane, and study lipid bilayer rigidity, protein membrane interaction by using a very powerful technique, fluorescence microscopy, spectroscopy, anisotropy imaging, anisotropy spectroscopy, etc. He also explained uh, that this type of study has potential to develop a new therapeutic strategy to cure the disease and a new approach to understand the origin of life. So thank you, Dr. Pavel Banerjee, for your excellent presentation. And finally, I like to say that honorable principals, students, and faculty member, once again, I like to say that we are all most grateful to all the speakers on this forum. We thank you for being with us in this afternoon. It's a great pleasure for us. Thank you very much.
Thank you very much, Dr. Pramanik. Now I am requesting Dr. Samik Mondal, former HOD, Department of Chemistry, Baharampur Girls College, to give valedictorian address of today's program. Dr. Samik, are you audible?
Yeah.
Okay.
It's okay. Good afternoon, distinguished guests, ladies and gentlemen. On behalf of the organizing committee, Baharampur Girls College, I, Dr. Soumik Mondal, Assistant Professor, Department of Chemistry, got the opportunity to provide the closing remarks. Dear participants, we have come to the end of our meeting. Firstly, I would like to start by thanking you all, the speakers, for their excellent talks, the session chairman for organizing the webinar. I would like to thank all the participants. Without your participation, ideas and discussion, this workshop would not have been the success it has. We are very grateful to you for taking time off from your busy schedules to attend this webinar. So, thank you all again for coming. This has been a wonderful webinar. I have enjoyed listening to the talks about the fine works in chemistry that you are doing. I am sure that the discussion about fluorescence spectroscopy will enlighten and motivate the participants, especially our students, to opt research as career. In future, we will try to conduct more seminars like this which could be beneficial for our undergraduate students. With these few words, ladies and gentlemen, it is an honor and pleasant duty for me to declare the workshop on fluorescence spectroscopy, its application in chemistry and benefits bioscience officially closed. Thank you all for your kind cooperation.
Okay, so here we formally call off today's program. Thank you very much, all the participants, respected chief guests, all the resource persons for their valuable time. Thank you. Happy New Year. All stay safe and stay blessed. Thank you.
Thank you. Bye.